Assalamu alaikum. We are discussing surface chemistry. Today's topic is Gibbs adsorption isotherm. Up till now, we have studied Freundlich adsorption isotherm and Langmuir's adsorption isotherm. Both of them deal with the adsorption of gases or liquids on the solid adsorbents. However, Gibbs adsorption isotherm deals with the adsorption of solutes on the surface of a solution or solvent. This isotherm was proposed in 1878 by J. Willard Gibbs, who was an American mathematical physicist. This adsorption isotherm provides us with a relationship between the surface concentration of solute or surface excess of solute, surface concentration or surface excess of solute, and surface tension of solution. It provides us with a relationship between surface concentration of solute and the surface tension of solution. Dear students, up till now we have discovered Freundlich adsorption isotherm and Langmuir's adsorption isotherm, and these two isotherms specifically deal with the adsorption of gases or liquids on the surface of solids. For example, the adsorption of carbon dioxide on charcoal or the adsorption of acetic acid from solution on the surface of charcoal. But Gibbs adsorption equation, it deals with the adsorption of solute on the surface of a solution or pure solvent. This isotherm was proposed in 1878 by an American mathematical physicist whose name was J. Willard Gibbs, and it provides us with a relationship between the surface concentration or surface excess of solute and the surface tension of solution. Let us derive Gibbs adsorption isotherm. Derivation of Gibbs adsorption equation or Gibbs adsorption isotherm. To derive this isotherm, we consider a system containing a solvent, a solution, and vapors in a closed vessel. The solution is separated from the pure solvent by a semi-permeable membrane. Here we have a semi-permeable membrane is present between the solution and the solvent, and these membranes allow only the solvent molecules to pass through them and do not allow the solute to pass. Now, the solution is also in dynamic equilibrium with the vapors above it. There is a dynamic equilibrium present between solution and its vapors. There are two movable pistons. There is a piston A, it is the piston A, which can be pushed down or up, and there is another piston B, which can be moved out or in. Now on this system, we have a system containing a solution that is separated from a pure solvent by a semi-permeable membrane, and this solution is also in equilibrium with the vapors of the solvent. There are two movable pistons, piston A, which can be moved down or up, and piston B, which can be moved out or in. Now we perform a cyclic process on the system, which is a 4-step process, and calculate the work done. Now we perform a cyclic process is performed on the system involving 4 steps. But first we suppose that gamma is the surface tension of solution, V is the volume of solution, pi is the osmotic pressure of solution, and the fourth property is S, which is the surface area of the solution. We consider these 4 quantities. Gamma is the surface tension of solution, V is the volume, pi is osmotic pressure, and S is surface area. Now we discuss the 4 steps which will be performed on this system. The first step will be step 1. We push the piston B outwards. Against the force of surface tension. We know that there is the surface of solution contain molecules, and these are also attracted in the downward direction, and these downward forces, they are responsible for surface tension. The same forces are present between molecules on the surface, so it is difficult to strike the surface. So we push the piston B outwards against the force of surface tension through a small distance ds. The surface is expanded through a small distance ds. Work will be done in this step, and this work will be performed against the force of surface tension. So the work done in step 1 is given by W1 is equal to minus gamma ds. Gamma is the surface tension of the solution, and ds is the small distance which is covered by the solution. Now during this process, as the surface is stretched, therefore the area of the surface area increases, and as a result the osmotic pressure will also increase, and the osmotic pressure, which was initially pi, now changes to pi plus del pi over del S, keeping the volume constant. And it is the change in osmotic pressure with change in surface area, keeping the volume constant. Now osmotic pressure changes to the value pi from pi to pi plus del pi or del SV. And it is the increase in osmotic pressure which has been caused by pushing the piston B in the outward direction. Now in the step 2, in the second step, we push the piston A in the downward direction, keeping the surface area constant, but the volume changes by a small element dV. We push the piston A in the downward direction so that the surface area remains constant, but the volume changes by a small amount dV. Now we know that solvent is moving into the solution due to the process of osmosis. We are pushing the piston against the force of osmotic pressure. Therefore, the work done in this case, the opposing force is osmotic pressure, which is given by pi plus del pi or del SV, and the increase in volume expansion is dV. Therefore, the work done in this step is given by W2 is equal to pi plus del pi or del S V ds into dV. Now it is the force of osmotic pressure and it is the displacement which has been covered by the system. Therefore, the work done is given by pi plus del pi or del SV dV ds into dV. It is the force and it is the displacement. So the work done is given by this amount. In this process, the surface tension, which was gamma, now it changes to gamma plus del gamma over del V S dV. Due to change in volume, the surface tension of the solution also changes and it assumes a new value, which is gamma plus del gamma or del V S dV. Yani del gamma or del V S means the change in surface tension with change in volume at constant surface area. In the third step, we bring the piston B back to its original position and decrease the surface area by a small amount ds. Now in this case, we are performing this work against the force of surface tension, which is gamma plus del gamma or del V S dV, and the displacement covered by the piston is ds. Therefore, the work done in this compression process will be W3 is equal to the force of surface tension against which we are performing the work is gamma plus del gamma over del V S dV, and the displacement is ds. It is equation number 3. Now during the reverse step, the osmotic pressure, which was initially pi plus del pi over del SV ds, it comes back to the original value pi. The osmotic pressure again comes back to the original value pi. It changes from pi plus del pi or del SV ds to pi. In the step 4, the last step, we bring the piston A back to its original position. We bring the piston A back to its original position and decrease the volume by a small element dV. Now here the work is done against the force of osmotic pressure, which has changed to pi. Therefore, the work done in this case W4 will be given by pi dV, equation number 4. Thus we have 4 work done. In the fourth step, now the surface tension, which was actually gamma plus del gamma over del V S dV, changes to the original value gamma. Now we have calculated the 4 types of work done. W1, which is due to expansion of the piston, movement of piston in the outward direction. The work done W2, which is due to movement of piston in the downward direction against the force of osmotic pressure. W3 is the work done when the piston B is brought back to the original position, and W4 is the work done when the piston A is brought to the original position. Thus we have performed a cyclic process on the system and we have obtained 4 different types of works. Now we know that in any cyclic process, sum of the all work done is always equal to 0. In a cyclic process, the total work done is always equal to 0. Therefore, we can write that in this cyclic process, we can write that W1 plus W2 plus W3 plus W4 is equal to 0. Equation number 5. Putting the values of different works from equation 1, 2, 3 and 4, we put the values into equation number 5 and we write here W1 plus W2 plus W3 plus W4 is equal to 0. Now the work done in step 1 was minus gamma ds. It is work done in step 1 plus the work done in step 2 is pi plus del pi over del s v ds into dv plus the work done in step 3 was gamma plus del gamma over del v s dv into ds, and the work done in step 4 is pi dv. Equation number 5, and here we have equation number 6 in which we have put different values. Thus it is equal to 0. This total work done will be equal to 0. Equation number 6. Expanding this expression, we get minus gamma ds plus pi dv plus del pi over del sv ds dv or dv ds, we can write anything, plus gamma ds. Now we open this bracket and we get gamma ds plus del gamma over del v s dv ds plus pi dv is equal to 0. Cancelling the common terms, we have here minus gamma ds and here we have pi plus gamma ds. They will cancel out. We have here plus pi dv and we have here minus p dv. The last work done was minus p dv and we get minus p dv and plus p dv. Sorry, W4 will be equal to minus pi dv. The net equation which we obtain is del pi over del s v dv ds plus del gamma over del v s dv ds is equal to 0. We shift the second term on right hand side and we get del pi over del sv dv ds is equal to minus del gamma over del vs dv ds. Dividing both sides by dv ds, we get del pi over del sv is equal to minus del gamma over del v s. Equation number 7.